there are no polyatomic anions, well, excluding cyanide involved, okay, it's going to be hydro and ic. So hydrocyanic, hydrochloric, hydrobromic, hydrosulfuric, okay? Does that make sense? When we have polyatomic anion within an acid, then 8, if the name of the salt, corresponding salt, ends with 8, we change it to IC. So chlorate, chloric. Okay? Does that make sense? I'm going to go through the table and illustrate it for you. If the name of the salt ends with ITE, such as chlorite, it's going to be OUS acid. So chlorite, chlorus. So this is what I am going to do. I'm going to highlight some of the, how to say, abnormalities, should I say? Okay. There you go. All right. So, if you have the anion that is either chloride or bromide or iodide or cyanide, so here's what you get. Ide and hydro in the beginning, IC at the end. There are no polyatomic anions, well, excluding cyanide involved, okay? It's going to be hydro and ic. So hydrocyanic, hydrochloric, hydrobromic, hydrosulfuric, okay? Does that make sense? When we have polyatomic anion within an acid, then 8, if the name of the salt, corresponding salt, ends with 8, we change it to IC. So chlorate, chloric. Okay? Does that make sense? I'm going to go through the table and illustrate it for you. If the name of the salt ends with ITE, such as chlorite, it's going to be OUS acid. So chlorite, chlorus. So this is what I am going to do. I'm going to highlight some of the, how to say, abnormalities, should I say? Okay. There you go. All right. So, if you have the anion that is either chloride or bromide or iodide or cyanide, so here's what you get. Ide and hydro in the beginning, IC at the end. Does that make sense? Good. Now I want to illustrate something here, just so you know. This rule isn't always applicable. There's a minor exception. So think of it this way. The name of the element is chlorine. right? So this anion is what? Chloride. Does that make sense? And this acid hydrochloric acid. You see that there is a syllable that is preserved in all three names. Good? We drop I-N-E. So here's the problem. You can put S6, but doesn't matter. Sulfur, right? So this anion, 2 minus. What is the name for it? Sulfide. What should be the name for the acid? Yes. This is an exception. Does that make sense? Okay? Am I clear? There's a hydrosilenic acid. I don't think you're going to encounter the same idea. Okay? Now let's take a look at the rest of the table here. So if you look at nitric acid and nitrous acid, what you do, what is the name of the element from which those are derived? Nitrogen, right? So you take the first syllable, am I making sense? And you make either the names for the salt, bless you, or the names for the acid. But here comes sulfur. So, first syllable is sulf, right? And it works perfectly fine with a sulfate or sulfite. But when you transition into the acids, you return to the full name of an element. You see that? Sulfuric acid. Same way you return to the full name of an element here. Not hydrosulfic, but hydrosulfuric. Not sulfic or sulfus acid, but sulfuric and sulfurous acid. Sounds good? Same idea with a carbon. Okay? Well, we don't have hydrocarbonic acid, so that's a different story. You're not using only the first syllable. You have to use both of them. And very similar to sulfur are phosphates. So phosphorus, right? Phosphorus gives you phosphate and phosphite. But it's not going to be phosphic or phosphorus acid. It's going to be phosphoric or phosphorus acid. Am I making sense? So while there are some logic in it, a lot of this is just traditional names that were accepted hundreds of years ago, and although they don't follow the pattern, nobody changes them. Okay?
Basically, they just got that way because they just roll off the tongue better.
I guess. So, HBr, which answer is that? C. because there are no polyatomic anions. This one, the carbon. So, how do you know that it's carbonic and not carbonous? 3 is the maximum number of oxygens that you can have in acids derived from carbon. Make sense? So maximum number of oxygens is going to be IC. And this one, so I'm going to give you an idea. Yes. Yes. Bromous acid. Because it is a sodium bromide. ITE changes to OUS.
So anytime you see oxygen, you know it's not going to be
hydro.
It's not going to be hydro.
It's not going to be hydro, no. Yeah, every time you see an oxygen. Bases, strict definition, when the Arrhenius base dissolves in water, it generates hydroxide anions. Okay? Thankfully, I never, ever tasted a base. Okay? I did feel them. They do feel soapy. Okay? And they produce blue color with a litmus paper, and they do turn phenolphthalein pink.
Are bases, like really strong bases, just as can they be like just as corrosive to metals as strong?
Not to metals, no. Not to metals. There are, so that's a good question. Strong acids are generally corrosive to metals. Bases aren't. There are some metals that can very, very slowly dissolve in bases, but it's not nearly as corrosive as acids are. Okay? Does that make sense?
What about like your teeth? Like if you
Oh no. It's going to kill your tongue. It's going to kill your mucosa. Teeth are going to be fine.
Or, yeah. So like for waters, like for a like if you're drinking a water that, so it would always be better to have your water be slightly like alkaline than slightly acidic. Like if,
from the standpoint of your body, not really. It doesn't, I mean, obviously, don't drink pickle juice and don't drink, washing soda solutions, but alkaline water and its supposed health benefits is a hoax. It is.
or like for example, mouthwash. I know like certain, like just when I've been like researching which mouthwashes to buy, I know like they say, I've seen online like if a pH is too low for the mouthwash, if it's acidic, they say it's it's not necessarily the best.
Yes, that is true. That is true. But one of the main components, the mouthwash that actually protects, is alcohol, about 20%. Kills bacteria. And the main source of acid in your mouth are bacteria on your teeth. So, and the amount of sugar, like table sugar, in whatever form, that you consume daily. So if you get rid of specifically, not carbohydrates, but specifically sugar, in a coffee, in a tea, whatever, I ran out of ideas. But if you reduce it, that will reduce the amount of acid produced in the mouth and therefore damage to the enamel. Okay.
Is it really bad to drink pickle juice?
What?
Did you say it was bad to drink pickle juice?
What I was referring to, it's acidic. Pickle juice is acidic. You can drink it, just not like by massive amounts.
Chase it with water so it dilutes.
Sure. Huh?
Yeah,
It's a great source. It's a great source of electrolytes, really. Okay, so the names for Arrhenius bases come from the name of the metal. Speaking of mouth, name of the metal: calcium, sodium, potassium, and OH group is hydroxide. Okay. First time I've heard Alicia asking me if I suggested drinking beetle juice. No, that would be too much. Okay, this one. I'm going to give you a hint. There is HNO3. So HNO2 should be what? Huh? OUS, and I can see only one OUS. D. This one, calcium hydroxide, very good. This one, B sulfuric. This one, A iodic. And obviously sodium hydroxide. Okay. Summary of characteristics. Now, yes, acids neutralize bases, bases neutralize acids. What is the easiest treatment? Like the cheapest probably, not the best, but the cheapest treatment for acid reflux? You don't have Tums, huh? You don't have Tums, but you do have like stuff. Baking soda. A little baking soda dissolved, like a teaspoon of baking soda per glass of water. It's going to help, but you're not going to feel great. You're going to get bloated. Okay?
A lot of people like they drink milk if they have it, but isn't milk slightly acidic, so that wouldn't really help that much?
Milk closer to neutral, they may be. So if you think about this, when you eat something, even when you drink water, you effectively dilute acid in your stomach. So the only problem is that you also increase volume and make the splash back into the esophagus more likely to happen. Okay? Baking soda is a neutralizer, but I did it a couple of times when I didn't have Tums. It helps from acid reflux, but you kind of feel like shit for half a day after that. You're bloating. Like you don't feel right in a stomach. So sour taste, acid or base? OH minus, chalky taste, electrolyte, both. They both are electrolytes. H plus in aqueous solutions. Perfect. Now, Bronsted-Lowry acids and bases, it's a more broad category. In other words, hear me out. I'm going to say something important. Every Arrhenius acid or base is also a Bronsted-Lowry acid or base, but not the other way around. Make sense? So, example of a Bronsted-Lowry base. Ammonia. Gas. When ammonia is dissolved in water, ammonia accepts an electron, okay? It accepts an electron. Where does that electron come from? The molecule of water loses it. So in this pair, water serves as the acid. Okay? Bronsted-Lowry base accepts hydrogen. Bronsted-Lowry acid donates hydrogen. Okay? So, which one of these two is a Bronsted-Lowry acid and which one is the Bronsted-Lowry base? Y accepts the proton, okay, and this is acid. What about this? Water is the base, again, yes. And hydrofluoric acid is, well, an acid.
Why would that reaction take place? Like, why would it occur? Because there's no outstanding, like, ions. Does that make sense?
Mm-hmm. So this is a really good question, and I'll explain why. If we look at the solution of hydrofluoric acid dissociates. So a little bit of it, okay, forms this. Does that make sense? Water, like if you take pure water, absolutely 100% pure water, it will do this. Making sense? So you can see that in both of these reactions, I put two arrows. They are reversible. They are in equilibrium. So at any given moment, a molecule of water can, quote unquote, absorb proton or not. Now, to your question, why would water absorb protons, right? Legitimate question. What is the charge on the proton? Positive. This is the molecule of water. And it has two lone pairs, which are electrons. Overall, the water is electrically neutral. Am I making sense? But these electrons will still attract this hydrogen. It's not going to be a chemical bond. It's going to be electrostatic interaction. Does that make sense to you? If water, okay, here's another example. So CO2, carbon doesn't have lone pairs. Okay, so it's not going to attract any hydrogen ions. Am I making sense? Yes or no? Okay. Awesome. So when you have a Bronsted-Lowry reaction between an acid and a base, you have conjugate pairs. So these are representative of the conjugate pair. HA can donate hydrogens. Does that make sense? When HA donates hydrogen, it becomes A minus. Can A minus accept hydrogen? It certainly can. So acid, base, base, acid. Because this can donate hydrogens if needed. Am I making sense right now? Yes? Good. Okay.
So the Bronsted-Lowry base will always become the conjugate acid,
Yes.
and the Bronsted-Lowry acid will always create the conjugate
Correct.
base.
Correct. Correct. It's called a conjugate pair. Okay?
And the conjugates will always be in the product side of the...
Conventionally, yes. Conventionally, we say that if you have on the left side a Bronsted-Lowry acid and a Bronsted-Lowry base, then on the right side you're going to have they conjugates. Does that make sense? But it is it all depends. You have to understand, it all depends. It's our terminology for convenience. It all depends what you are hold on. which way you write the reaction. What you put as your reactants, what you put as your products. It is like what I prefer personally to use. It's a conjugate pair. Okay? So, for instance, here, we write the reaction in which hydrofluoric acid interacts with water. Okay? So, in this case, fluoride is going to be a conjugate base for hydrofluoric acid, and the term is hydronium cation. Okay, will be conjugate acid for water, which is a base. Does that make sense to you? Now, from the chemical standpoint, it's a small comment from me. From the chemical standpoint, this, like for instance, we say, oh, HCl dissociates into hydrogen and chloride. This is incorrect. There are no, because what is a hydrogen atom without an electron? It's a proton. Make sense? Single protons do not exist as protons in the solution. The correct way to write it down would be this. HCl reacts with water, producing hydronium cation and chloride and I. Does that make sense to you? But in many cases, we just disregard that water on the left and H3O plus on the right, and basically make it equivalent SU2 to hydrogen. Okay? So, this is another example. Sorry. On the left, what serves as the base? What accepts protons? Huh? Ammonia, right? It's a base. And water donates protons, so that's acid. But on the right, NH4 plus, the ammonium cation, can donate hydrogens if needed. So it is an acid, and OH minus is the base. For HBr, what's going to be the base? Hydrobromic acid. When interacts with water, what's going to happen? Br minus plus H3O plus. If the HBr, what does it do with its hydrogen? Gives it away, right? So this is acid. What is the conjugate base then? Yes. H2S. HS minus. Hydrosulfide anion. For carbonic acid, what's going to be the base? Yes. And this is the most important acid-base equilibrium in the human body. Okay? This is how humans produce acid for the stomach or base for the intestine. What will be the conjugate acid for nitrite anion? Yes. So here's just like sort of a, I'm going to decipher the first one. I'm going to deliberately put H3O plus. So what we have is HNO2, right? And water. Does that make sense? Yes? Good. What's going to be the conjugate acid for NH3? NH just 4 or NH4 plus? Plus, because you're adding hydrogen cation. 4OH minus, what is the conjugate acid? Water. Let's circle acid-base conjugate pairs. First, is that a pair? Yeah. I'm going to skip second. Okay, I'll explain why. Third, is that a pair? No. Fourth, is that a pair? Fifth, is that a pair? So, why I have reservations about this? Because this is what's going to happen. Check this out. Carbonic acid will dissociate into this. Make sense? Carbonic acid is extremely weak. And it means that if we would compare these arrows, this process will dominate over this process. Am I making sense? In order to do this reaction, this is practically impossible. This doesn't happen, or happens to a very small extent. Does that make sense? So if you would ask me, no. No for number 2. What are the pairs? I mean, nitric acid and nitrate, right? And ammonia gas and ammonium cation. Good? So, difference between the strong and the weak. Strong acid, complete ionization, complete dissociation into ions. Weak acid, incomplete, so this should be like this. It's an equilibrium, okay? So you have some dissociated and some are not. Does that make sense to you? Everybody? Good? Okay. So this is an example what happens to hydroiodic acid in the solution. It's fully dissociated. So what I want you to pay attention here, check this out. This is the concentration. This bar represents the concentration of HI as the formula unit, okay? When it dissociates, let's say you have 1 mole. 1 mole of iodine, of hydrogen iodide. Are you with me? When it dissociates, you have 1 mole of H3O plus and 1 mole of iodide. Weak acids, they dissociate incompletely. See that? So if this was, I don't know, 1 mole, I don't know, 0.8 moles. If 0.2 moles dissociated, 0.2 of hydronium contains 0.2 of fluoride. Okay? Does that make sense? These are strong acids. Okay? I have no idea why they did not include, no, they did include hydrochloric acid. Okay, but that's pretty much, for our intents and purposes, that's enough. There are some organic acids that are fairly strong, okay? But we're not getting into these weeds, okay? And you can see, how strength falls down as we move down this table. Little sort of common knowledge. You see this, phosphoric acid. Anyone drinks soft drinks such as Diet Coca-Cola, Pepsi, yeah? Read the ingredients next time. It contains phosphoric acid. Do you know what Coca-Cola, preferably Diet Coke, is really good for? Rust removal. It is strong enough to do that, and if you need to clean the battery clamps, works like a charm. They get sticky, but cleans all the rust. Tried it myself. Okay. Bases exclusively these ones. Okay. Now, if you look at the periodic table, you may notice that the metals of the group 1 that are included in this list are lithium, sodium, and potassium, right? There's no rubidium, there's no cesium. You know why? Because these metals are ridiculously expensive, and nobody's going to produce bases from them for like commercial use. If you just need a strong base, lithium, sodium, and potassium would suffice. Okay? So barium and strontium hydroxide are really strong bases. I want to make a comment on calcium hydroxide. It is a strong base, but its solubility in water is not great. Weak bases, ammonia, washing soda, baking soda, sodium phosphate. Okay? So, for example, in biological research, phosphate is often used to stabilize the pH of the solution because it will form a great buffer. So, strong or weak, HBr. A good way to remember, look at periodic table. 17th group. You see fluorine, chlorine, bromine, iodine. Except for fluorine, other three are strong. Yes, strong acid. Then, keep looking at the thing. Oxygen, nitrogen. Sorry, nitrogen, sulfur. See that? With the maximum number of oxygens. HNO3 is strong. HNO2, though, is weak. Now, H2SO4 that we have on the list is strong because 4 is the maximum number of oxygens. But H2SO3 is weak. Sodium hydroxide, strong base. Now, copper hydroxide is not a strong base at all. Now, this is kind of absurd. Identify the stronger acid in each pair. So we have to go back here and look at the list that is presented to us. I believe you can do that. So, strong, yeah. Nitrous acid should be stronger. Let's check myself here. Yeah. Yeah. It's considerably stronger. Hydrobromic acid is stronger, and hydronium cation is stronger here. Does that make sense to you? Okay. So here's the deal. We're gonna talk about equilibrium itself, define the equilibrium, and see how it is regulated, and then we're gonna stop. So here's an equilibrium. You have a forward reaction between hydrofluoric acid and water, producing fluoride anion and hydronium cation. Clear? But at the same time, fluoride anion interacts with hydronium cation, generating hydrofluoric acid and water. When the rates of the forward and reverse reactions are equal, this is the equilibrium. Does it make sense? Okay? That means that the concentrations of products and the reactants, concentrations do not change. One of the examples that you can think of is a grocery store. When it opens, people come in, but there's nobody inside. At some point, conceivably, the number of people that walk in and the number of people that walk out are going to be the same, so the number of people inside the store will not change. Okay? So, before equilibrium is reached, the concentrations of the reactants and products equal or not? Before, not. They're not equal. Concentrations are still not equal. Okay? So, rate of the reaction for reactants, faster or slower than the rate of the reaction for, basically, the rate of the forward reaction. Is it faster or slower than the rate of the reverse reaction in the beginning? Faster. At the equilibrium, oh, it's a different term. Before equilibrium is reached, the concentrations change or don't change. Before the equilibrium is reached, the concentrations of reactants and products change or not before the equilibrium is reached. This is the concentration. You see? They are changing, yes. When they stop changing, the equilibrium is reached. So at equilibrium, the concentrations do not change, and the rate of the forward and the rate of the reverse are what? Equal. Okay, let's stop right there. Let's stop right there, and we're going to talk about the Chatelier principle next time. Sounds good?